Okay. So, question 1, tutorial week 9, and we know that we will have some SageMath as well. So last week is enough for your assignment, but this week also will be a practice for your assignment, second assignment. It's 16 mark for second assignment. I'm pretty sure that all you guys, you will get 16. Because what you need just improved, especially the improved Euler. Last week in this Python file, IPYNB file existed in the canvas, and also improved Euler method here in the SageMath file. What you need for Hume's method, you just need to adjust it in according to the Hume's method. For the Hume's method, please do not use the Wikipedia. It's just again the improved Euler method. The Hume's method is coming from the literature of this course. Euler's method is also we have seen last week. We investigated broadly. Question 1 says that the first order of the Taylor series is the improved Euler method, and prove that its local truncation is a number which is something times h cubed. According to the definition of the improved Euler theta, you see that this guy, the new y is dependent on the older y plus this guy here, h over 2 times like this f, which we will call it k1. So here is k1, okay, in the SageMath. And here, this guy, f xn plus 1, yn plus 1 star is the actually k2, this guy. All right. So, so it's kind of obvious that why is it like h cubed? Because we've got this guy, and this guy has got yn plus 1 star, h in it, and this guy, and this f of the like two terms here, it will have another h if we expand it by Taylor's series. So we will have 3h. But let's have a look at in details. So I've got this bracket, and what we don't know about this, this guy is y prime, this guy we don't know. So f of xn plus 1, yn plus 1 star. So xn plus 1 meaning is this. The yn plus 1 is written here, and I've written it here. If I expand this one by using the first, just one order, the zeros term and first term, the term number 1 plus OH squared. Okay, I can use the two-dimension Taylor series, and I can, instead of this one, I can get this one. So this is coming from equation 1, lecture note 8. Not lecture slide, a lecture note. This is the lecture note, week 8, course note. So question 1 is this guy here. So over there, k is just again same as h here. They are the same. I equals 0 is f, just this guy. So this will be 1. I equal 1, this guy times f. Then we didn't write I equal 2. This guy, ENHK, or we have written OH squared. Okay. Now, so I can write this guy. So therefore, I can sub this red in for this. So yn plus 1 will be equal yn plus 1 over 2. I put h inside bracket. It will be h times this guy f plus. So instead of this guy, I write this one. So the red one, okay? H, but I multiplied by h, everything. H times f, which is the same as these two guys. H squared. So again, these guys, okay? And OH squared, if I multiply this guy, OH squared by H, it will be O, big O notation of H cubed. OH squared is something times H squared. If I multiply it by H cubed, it will be OH cubed. So I think the monitor is visible for you guys. Now, what is this? This two is like two of them. See this guy, h squared plus h squared times this guy is d over dx f, total derivative of fx and yn, which is equal to this y double dash. You don't believe me? Okay, no worries. Then you can have a look at the again lecture 8, week 8. So you see that y double dash d over dx, this guy, because this guy is y prime itself. So if I take a derivative, it will be y double dash. So y double dash is this guy. So you see this guy, it is same as this one here. So that's why, since we are good people, we can do some simplification. Yn plus 1, yn 1 over 2, 2hf or 2hy prime. H squared y double dash xn, okay, plus OH. So the local, anyway, the local truncation is big O notation of H cubed. Okay. Can you prove that for the Runge-Kutta? Yes. The Runge-Kutta's order is, you will have to proceed with this one, number 1 by I 0, 1, 2, 3, 4. Okay. Then you can prove that its truncation will be h to the 5. Something times h power 5. So Hume's method is the same thing. Euler's method, you have to use just I equals 0. So solve this. Question 2, like the previous last week's question, y prime, this guy 2x minus 3y plus 1, y of 1, initial value is this guy. So the analytic solution is given to us. Nevertheless, we could obtain it by SageMath. So in the SageMath last week, which is uploaded in the canvas, you can see that we can obtain this guy. Says that, so Runge-Kutta method, which is a fourth order numerical method, is this guy. So look at this one. So we can choose for k different h, and we can adjust this guy here. But so you can obtain several of the fourth order methods, but we want something like fourth order, but in the same time similar, as much as possible, simpler, sorry, not similar. So we've got this one. So local truncation is this guy, H5, that's it. So it says that local truncation in terms of C and H will be this guy. So H, so generally we don't know H, we don't know C. Nevertheless, C can be, starts from 1 initial value up to destination X. Okay, so C will be between 1 and destination X. The order of derivative order 5 can be obtained from this guy. If it's not there, if this one analytic solution is not given to us, so then this guy can be obtained from this y prime. So you can take y double dash y, but it is also depending on y. So it will be a little bit difficult. So part A is the question for children. So it's not for us. So you just do this. Okay, nothing. Now, part B says that h is 1/10 y of 1.5. So C, where is C? So C is between 1 and 1.5. Okay, so you can decide which C you should put here. The upper bound will be C. To get the upper bound or the maximum value, exponential of minus argument is decreasing. So you will choose, so between C and 1.5, you will choose C equal 1. So if you put C equal 1, this will be at more 1. So that's why this guy is 1. And you just sub h by 0.1. So if I do this simplification, absolute value, so this negative will be removed. So this will be this guy, which I just checked by SageMath. Okay, part C, approximate y of 1.5, step size 1/10. So step size 500. So 1/10 means 5 times Runge-Kutta. 500 means 10 times Runge-Kutta. Even for doing 1 time Runge-Kutta, it's not easy. So you really need to implement this Runge-Kutta in any soft computing. So in some programming languages, you can find inhibited commands. Maybe in MATLAB or Maple, there are some Runge-Kutta, so you can use them. But so for your assignment, you have to implement it. You are not allowed to use inhibited functions. Whether for the ODEs method or for the Hume's method. For none of them, you are not using inhibited commands. But as we saw last week, sometimes it's possible to see that the algorithm that, most of the time, the algorithm that you are yourself developing your own algorithm, it will be faster than inhibited commands. So question 3 is this guy, y prime of this simple things. The analytic solution is obvious because the characteristic equation is r equal to, so the analytic solution is this guy. It is initial value problem because the starting point condition is given to us. So approximate this guy, Runge-Kutta, from y of 1/10. So with step size, 1 step size. So y of this guy, so it means h should be 1/10. So the bound for B is this. So y of 5x or c is 32e to the 2x. And we've got this guy. So the upper bound must be like this. So we have this guy. So c is between 0 and 1/10. So now e to the 2c is increasing function. So it gets its maximum when c is the maximum. So what we do is just substitution. All right, let me check something. All right, so this should be, so you see this guy here. This should be 32 exponential of 2 times this guy. What is this? So I think I mixed with the other question here. This guy. So that's right. So this is right. This is right. All right. So what now? Let's go to the SageMath. It's enough. All right. Now, so here. So SageMath part of the week 9. Before going to do the question 9 and question 2 and 3, so there are some 2 examples in the course notes in maybe week 8, the 3rd or 2nd last PDF. Let's have a look at them. It has been written there, the answers, but we can have a look at here as well. So maybe those solutions in your course note, it's implemented in different languages, but SageMath, we will do it SageMath, or in other language, in other words, we do it in Python. So this guy is, what type of ODE is this? Can you determine what the ODE is? How can you solve this one in? Yes, separable. Thank you. Separable. So step size, let's do step size this one, 1/10. Okay. XY, this is the way that we define the XY can be variable. Now, I define F. F is just, this is this one OD is given to us like in the standard way. It is compatible with our criteria. F is equal to this guy. Improved Euler method is like step size 1/10, and the destination we will see. Now, PTS is the list of the points or list of the vectors. So list of the vectors is called tuple in Python. So in Python, we have list, we have array, we have vectors, we have tuples, we have dictionaries. Some of them have more facilities like dictionaries, but they will get lazy or slower. Okay? So depending what you are doing, you are using accordingly one of them. So list of the points or tuple here, x equals 0, y equals 1, the initial condition here. So PT is 1 point or 1 vector xy here inside this guy. So we will put this new point, what we are finding in future inside loop, we will put it in this list. This point is like, this point is itself is a vector, which is like this xy. So then we will assign, or we will put or save this point inside the big list of the points here. So appending a point in the list, it's been like explained in my YouTube videos. All right.
So it points a vector on vectors.
Points is list of the vectors.
Yeah.
List of the vectors. So what is this vector? Vector is this guy, which is variable, which is it's changing. We are updating x, y anytime. So let's go inside to the loop. So you can put range starting from 1, this guy plus 1. Or you can put range just this guy. Okay. Why do I do this? Because, as I said last week, because I want to confuse. Okay. That's one reason. Second thing, I want you to think. Sometimes you see that there is no +1, there is no 1. So b minus x, what was x? 0. Okay. What is the destination? 1. So 1 minus 0 is 1 divided by h. What I choose for h is 1/10. So 1 divided 1/10 will be 10. So here range is between 1 until 10 plus 1, 11. Okay. 1 until 11, so it will be repeated 10 times. Okay. So when we write in 11 in Python, it will stop at 10. Okay. But if it was in MATLAB, it would stop in 11. Julia is also would stop in the 11. Julia is the name of the Python programming language. All right, so K1 or F, K2 is that guy F of like xn plus 1. This second guy is yn plus 1 star. What is yn plus 1 star? I have written it here explicitly instead of writing yn plus 1 star. So by having this K1 and K2, I can obtain the new y. It's not long. So we don't write yn plus 1 here, yn here. So it will be updated. It will update by itself. X is also updated. So the new point will be after this will be x, this guy plus h, x plus this guy. And the new y will come here. And this vector will go to this. Okay, so after collecting our list, so we will collect here by these two things, two new lists. I will collect the X collections. Second guy will do the Y collections. So we will have this guy. So returning X and Y, I will get 1/10, 2/10, 3, 4/10 until 1. And correspondingly, I will get my y. Why do we do this? Because I want to plot them. Could I make this one a little bit like more beautiful? Yes, it's possible in programming. Okay. So even writing this one, it took me like a lot of time. So I developed these things in 2020. All right, so we have this improved Euler method. So for Hume's method, what you wanna do is this. So improved Euler method, we have written something like this. So it has like just K1. So you have seen it in Python. In Hume's method, you will change this F. So initial value, of course. Same. You will adjust K1 and K2 probably. And same thing, and same thing, the rest same, and you will get your result. And you will plot it, you will get the answer of y of 1, y of 2, y of 3. All right, so what happens if I plot that? So if I plot, so this is the improved Euler method. This is a function that we have developed by ourselves. It is not inhibited command. So R is the list of this T. What is this? Output of T is this guy and this guy. Okay. So output of T is the two parts. It has two parts, two lists. The first list will be my X. The second list will be my Y. So in range of 9. This time instead of writing that, so it will be 0, 1, 2, 3 until 9, so 10 times. Okay. So maybe this should be 10. I'm confused. All right, can I try? Yes, it should be 10. Okay, but you will adjust. All right. And this guy must be 5, I think. This guy should be 4. Okay. So let's put this one 9, so you can think about that. All right. So what is this? Improved Euler theta with 1/10. This guy is like lazier step size, 2500. So you see that obviously the blue guy is the 25. So 1, 2, 3, 4. Okay, so 25s have 75, 1. So 4 of them. So we can plot this as this. So let's make it a little bit better. So that ODEs upper written it here. We can solve it analytically. So the analytically, after solving, I will get this guy. I don't want to simplify it. I don't have time. So what I do is this. I multiply everything by 2, which I did it here. Then it has y squared. I will make it square root. So this guy will be square root of everything after multiplication by 2. So this, I will plot the analytic solution at this interval between 0 and 1.2. It was possible to plot it between 0 and 1, but I want to see more, like somehow I did zoom out. Now, improved Euler method, again, 1/10, 2500. So you see that the green one is 2500. The blue one, which one is the blue one? Blue or red one is the 1/10. So this guy. I know, sorry. The blue guy is 1/10. And the red one is analytic solution. So as the step size is finer, it is getting to be closer to the analytic solution when we plot it. That's beautiful, yeah? Now, what happens if I do the same example? Again, it's given in the example 4 in that course note. So, but rather than using improved Euler method, we can use Runge-Kutta. So XY variables, this is another way that you can define your variables. The difference of this guy here, XY, that's generate a polynomial with the coefficient of the Q, rational numbers, where XY are their variables, 2-dimension polynomial. The algebra people need this command. So that's why algebra people, they use this. So simpler way of writing XY variable is this guy, or just writing this guy without writing X equal that and Y equal variable. So just writing variable Y, variable X. Function, Runge-Kutta, PTS, X, Y. So again, same stuff. Now, look at this here. The only thing that we can change is here. K1, K2, K3, K4. I'm sorry about that. Okay. So because Runge-Kutta, it has 4K. So after having these k's, k1, 2, 3, 4, you can update your y. And x is obvious. So you can get your results here. So we can choose like lazier step size. Instead of 1/10, you can get 2/10. All right, so we can plot it. You see that here? Step size finer, it is closer to the analytic solution. So this example will enable you to get your implementation easy. Question 2 of tutorial week. So it's given to us, this guy, analytic solution. So approximate y of 1.5 using Runge-Kutta. So Runge-Kutta is written here. So step size 1/10, I can get this guy. Step size 500, half of that, I can get this guy here. Upper bound for this guy. Upper bound part B, local truncation of this guy. The maximum of the local truncation is this one. Now, solution in one step is this one, if you remember. I just copied from here. Solution in the twice finer step size is this guy. I have written it here. I just copied and pasted here. So if I divide them together, so I will see a 1. So it means the step size 1/10 is already good enough. If I do it like 25, so the last one is, so the last one is not working very well. But okay, it's okay, because instead of y of 1.5, I have used I tried to use y of 2. Anyway, so I can get, and I can try use again Runge-Kutta for that. So the analytic solution is instead of writing this guy here, y of this, you can get your analytic solution by using this DE solve. So you see that, so step size finer, so it will be closer to the analytic solution. Question 3. So analytic solution is this guy, okay. Y prime of 2y, initial condition. Part A, approximated, y of 1.5, 1 step size. Runge-Kutta again, this guy here. So you don't have to write Runge-Kutta over and over. Because if you have 1, so you will be fine. So Runge-Kutta in 1 step size, you get this guy. Part C, compare the error y1 with the error bound. So the upper bound of the this function, as we saw, is this guy, this formula. So absolute value of h to the 5 times 32 times exponential of 2c, or 2 times 1/10 divided by 5 factorial. So the upper bound is this guy, 3 points. So this is the upper bound of the local truncation. Now, so we want to, so obviously, if I have this one, and if I've got the exact solution, the absolute value of the exact solution, and this 1.2 must be less than this. Okay? So exact solution is coming from this guy, e to the 2x, e to the 2 times 1/10. So if I print it, I will get this one. So what is this? So can I put this one here? Oh, no. Okay. So yeah, I copied this guy and I put it here. So So the exact solution is this guy. So error is absolute value of exact solution. So actual error will be this guy. So actual error 2 times 7. What was the upper bound for error? Was this guy. So upper bound is 3.25. But the actual error is this guy. So definitely that this should be more than this 2.7. 10 to the minus 6, 10 to the minus 6. Runge-Kutta twice step size, twice finer. So you can get this one. It's given, so you can do the exact absolute value of this one is as well. It must be even less than this as well. Part E, verify the global truncation error for the RK4 method is of order H to 4. So the solution of the one step size is this guy. The solution of this guy is 2 step size is 1.2. The exact solution is coming from here. So absolute value of the exact solution is solution 1 step, absolute value of the solution, exact solution minus solution times minus 2 step, solution of 2 steps. Okay, exact solution minus 2 step size, exact solution from 1 step. Okay, h power 4, h power 4. So one of the h is the like twice finer or half of the other guy. So if I have this h and this h, if I divide them, okay, that will be 2 power 4. Okay, so that's why we expect to get 16. Okay, in the order of 16. Okay, which is in the order of 16. Do you have question what I said? So look at this one. H1 is 110. H2 is 500. So OH14, OH24. Okay, so OH14 is something times H1 power 4. So OH24 is something else times H24. So let's cancel something and something else. Okay. Approximately it will be H1 4, H2 4. So this means 1/10 power 4, 500 power 4. So instead of 1/10, you can write 2 times 500. So 500 power 4, 500 power 4. Okay, you can cancel this and then it will be 2 power 4. So 2 power 4, 16. So that's why we should expect this number. Now, you see that this H1, the global truncation is H power 4. Okay. The local truncation is H power 5. Okay, so did we use Runge-Kutta? So this one, OH1, since it's 1 step size, it will be 5. And H2 must remain 4. So this guy, if I do this guy, 5 and 4, then I must get 5, 5, 4. So then I should get 2 power 5 times 0.05. So in fact, since the first one is 1 step size, it's local truncation. The other one, 500, since it is 2 step, it is not local truncation. It is global truncation. Okay, so we should get this one. Nevertheless, 32 times times 5/32. But this might be, so you should get, if you divide that, this should be 5. Okay, this should be 5. Okay, but you get better than 5, you get 14 or 16. Okay, this means your Runge-Kutta is even better. But if you think both of them acts as local truncation or global truncation, if you consider both of them global truncation, both of them means h power 4, then you should get this 16. You should get 16. Okay, so more or less we get that. So here we get almost 15 or close to the 16. Now the last thing, and I will finish it after this. If you use your Hume's method or Euler's method, for example, you expect that the precision will be when you divide them. The local truncation should be in Hume's method. What? We just did it. Question 1. OH3. So if you divide them, you see that okay, it should be something like if you took it will, so the step size is 1/10, 100, 1,000. Okay, so you might get bigger number. So you say that okay, 10 power 3, 1/10, 100. What's the difference of like 10 times of the other one? So it will be 10 power 3. So it means 1,000. 10 power 3 is 1,000. So if you divide them, it will be 1,000. But you might get bigger number. It doesn't reject your assumption. It says that okay, this numerical method works even better than what you expected. All right. Okay. Have a good day ahead.